Let's take them point by point and start covering them. Metallic versus ionic crystals. Now, we will say it like this. Well, I'll write down the distinctions here and similarities because we don't have to write them separately. We will list out the similarities in a separate column. Let's try to write down as many as we can. What is similar? Well, both have a regular lattice structure. Both are crystalline, both have regular lattice structure. Of course, that is something which is common between metallic and ionic crystals. Yes. Anything else? A very obvious distinction is that they are bound by metallic bonding. And they are bound by ionic bonds. Then lattice points. And lattice points in metallic crystals are metal atoms. And what happens in metallic bonding? Metal atoms release their electrons, they delocalize them, and they just sit. Electrons are moving around. So all the lattice points have similar positive charge. Electrons which are delocalized, the sea of electrons, that carries the negative charge, but all the lattice points have similar positive charge. And in this case, the lattice points, not all I would say, the lattice points have positive as well as negative charges. Lattice points have both positive and negative charged particles because there are cations as well as anions. Since they have delocalized electrons, they conduct electricity in solid state, and they are insulators of electricity, usually in solid state. Why? Because their ions cannot move, they cannot leave their positions, so they can't really conduct the electricity. That makes sense. Anything else? Well, can we talk about malleability, ductility? Yes. Metallic solids are malleable and ductile. They're also sonorous. Malleable and ductile, sonorous. Sonorous means they have a typical bell kind of a sound, a metallic sound of clinking. Ionic crystals don't have that. So they are brittle. If you beat them by hammer, they will just break like glass. You can't draw wires. They are not malleable, not ductile. They are brittle, they are hard, and they are non-sonorous. Take salt crystals and try to crush them, bang them together. You won't actually hear a clinking sound of metal or something. It's just a dull thud, nothing else. So they are brittle, they are hard, and they are non-sonorous. Yes. These are 4 points of distinction. I could give you many more points. Metallic solids are never transparent. Metals are always opaque to visible light. Ionic crystals, there are rare ionic crystals which actually could be transparent, like AIIMS, for example. They could be transparent. Potassium nitrate crystals are lovely transparent crystals. Needle-shaped crystals of lead acetate, ammonium acetate are lovely transparent crystals at times. So they could give you transparent crystals. Their crystals may be transparent to visible light. There are cases, and in none of the metallic solids you would ever find that a metal is ever transparent to visible light. Yes, these are, and you could give examples, metallic solids like iron, cobalt, nickel, gold, any metal. And ionic solids like NaCl, RbCl, KBr, CaSO4, all these are. So I have given you six points of distinction between metallic and ionic solids. Do they have any similarities? Well, they have sharp melting points. They both have sharp melting points. They melt at a unique temperature. Yes, that's very beautiful. Anything common? They both conduct electricity in molten state. If you melt them, a molten metallic substance also will conduct electricity, and a molten ionic crystal also would conduct electricity. Wow. Anything else? Yes, a fourth point. They're usually hard. They're usually hard. A metallic crystal like iron or titanium is hard. I mean, there are cases like mercury or alkali metals which are soft, but if you just leave them out, most of the metallic crystals are pretty hard, and most of the ionic crystals are also pretty hard. So yes, they do have that in common very much. These are 4 points of similarities between metallic and ionic crystals. Explain that ionic solids are hard and brittle. Why should they be hard and why should they be brittle? That's a very beautiful and a very simple explanation. Let me first draw a metallic solid for you. Well, we have cations, 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 cations. Is this what? An ionic solid? Crystal? Well, there are anions also. Let me draw them for you. You have anions, you have anions. What is this? This is cheap time pass. No. It's a very beautiful thing I'm doing. You should also do the same. Make this in your notebook. Fine. This is an ionic solid. Opposite charges, strong Coulombic attraction. Each cation is surrounded by many anions. Each anion is surrounded by many cations. So, they're all very tightly held together. Great affection, great bonding. And that is why an ionic solid is very hard, because every cation is surrounded by a number of anions and every anion is surrounded by a number of cations, and they're all bound to each other by strong ionic attraction. Yes. That explains why they are hard. Why are they brittle? Well, that also is very, very interesting. Try to, bring a hammer, okay, and just try to beat them. Let me try that. Say, you said that fine, I have a hammer and I am going to, strike this hammer. I'm going to beat them. Fine, beat them. What happens? The moment you strike them, because they're held by strong attraction, they will not move. And by any chance, if they actually move, if you push really hard, you could move them down. And when they move down, what happens? Even if they move down slightly, you would discover that once they move down, it is cation versus cation, anion versus anion, cation versus cation, and suddenly you would discover that there is going to be a fraction. Why? Because they will repel and they will just jump away. So the entire layer will rupture. Whatever was actually attraction would suddenly turn to repulsion, and with a cracking sound, they'll just break away. Not one or two, everything will break off. Oh my God. And that is why they are brittle. So, hardness because attraction is high, and brittle because all that love turns to hate if you push them by pressure or force. Because opposite charges, instead of opposite charges, like charges come opposite to each other and they just repel away. That explains the brittleness of ionic compounds.